Hi, welcome to part two, basically, of this recording concerning the project related to the orbit of Mars. So you have a bunch of data, and at this point, when we started collecting them earlier, basically I drew point M1 and M5, but I went ahead and finished the other points. M2 is going to be here, M3 is going to be here, M4, M5, we already did that, M6, M7, M8. And some of you duly noted that most of the points are actually on this side, with a couple of points only below the in this case the vernal equinox. I just hit it in here. So the sun is in the center, and what you're supposed to do next, you draw the path of Mars going from M1 basically through the entire path in here throughout this period that where the data was recorded. Obviously, you don't have all of the points, so you're going to do your best to draw a smooth path. That's the key. The word is smooth. Now, as a to practice drawing this path, try to draw it first of all in the air. Don't draw it right on the paper, because if you do that, you may not have it as smooth as you want, and then you try to correct it and ruin it. Part of the problem is you're going to probably draw from M1 to M2 a line and then another line in here, and then you realize there is a big gap between M3 and M4, so it's going to be a problem. So in other words, and you don't have to go from M1 to M2, by the way. There is an M8 in between them. So in this case, it's a path at the legitimate position of Mars. So you draw a whole path in here, and it should look more or less like a circle. Actually, it's an ellipse, and we'll see why that is. So I'm going to have a tool in here, which is this ellipse. I'm going to draw the ellipse. I'm going to start it in this location here somewhere, and then in here, and then I'm going to have 2 points in here. As long as my ellipse passes by some points in here, I'm in good shape. So I'm going to put it right in here to include as much as possible points in here. Now, obviously, this path is not good, so I'm going to take the point. I'm going to take the point A and start playing with this position until I get it so that it passes by as many points as possible in the graph in here. So obviously the point D in here probably need to move a little bit to include at least path A, M1, and then this one includes, and where is the other point is B basically. No, I don't want C, Control Z. I don't want to move the point C. I really want to move the point B, this one in here. So I'm selecting it manually. And that is the one that moves my path to get it to orient as close as possible. Obviously, you're doing a project, and the project, I don't want the C again. Why is it doing C? I want the A, because they are too close from each other. That's why I could fix C. Okay, I think this is a great path. Okay, this is a great path. This is the actual path that I'm looking for in this case, that passes by the vast majority of the points. Obviously, point M8 in here is not exactly where it needs to be. And so is point M5, not even M4 also, but it's very close from where the path of Mars is. So basically, you're doing an evaluation in this case. Okay, you're supposed to go from the sun, use a ruler, and find the closest point on the path to this one. So you take a ruler basically and you start moving it around. Okay, make sure it's centered on, or at least the starting point is on the sun and the ending point is on the path of Mars. Okay, I'm going to check this path and make it red so that I know that this path is red. Okay, just to indicate that I'm talking about the path of Mars. So again, you take the ruler starting from the sun and you try to move it around to find where the closest point is. And in this case, it turned out to be near M4. It doesn't have to be one of the points that you measured, by the way, as long as it's closer to one of them. It doesn't have to be even close, as long as it's the closest point to the sun. Okay? That is your perihelion. The aphelion should be the opposite to that. Okay, for Mars when it's the furthest from the sun. Okay, so you take this distance, call it R2 or RA for aphelion, take this distance and call it R1, or in this case RP for perihelion. And then you take the difference between these two, and you take the, actually I have the calculations in here. With GeoGebra can do all of these things for me, okay? And you take their sum, which is actually the major axis. This is your major axis. Your minor axis is going to be somewhere in here. And at the end of the day, basically, this is the path that you have found. This is you don't really need the minor axis in this case. All you need is just the major axis. And you calculate the perihelion and the aphelion. And after that, you do the calculation. That is actually, let me find it. Yeah, actually, you're supposed to do these measurements, as I said, and find the eccentricity of the orbit and compare the eccentricity to the known value of the eccentricity of Mars, which is 0.09. And after that, you're going to basically see how much error you have, and you conclude this is again what I was talking about. Of course, this is well exaggerated. This is far, far more eccentric path than what the actual path is. From the curve, I'm sorry, I was not sharing. Yeah, let me go back into the calculations that I was showing. Again, the eccentricity is just a difference between the aphelion and the perihelion, and over the sum of the two, which is a major axis. And in this case, it's going to give me the value for the eccentricity. You're supposed to compare it to the known value of Mars, and you're going to come up with an error. Again, this is the path of an elliptical path of Mars exaggerated. It's not that eccentric as you can compare the two figures. I mean, this one is far flatter than this red path in here, okay? But the point being in here, this is your aphelion. I'm sorry, this is your perihelion. This is the closest from the sun. And this is your aphelion, the farthest from the sun. And this path, obviously, it's not lined up, at least according to this curve in here, where the x-axis is the major axis. This is the major axis in this case. So the minor axis should be somewhere in here, perpendicular to this one, passing by the center of this whole perihelion, which is slightly off of the sun, one point C in this graph. Anyway, so this is the calculation, and you're supposed to compare it to the well-known value of Mars. So this is how the path should look like. Once you have it, this is how the path should look like. Let me do something in here. Let me see. I know the path in here is called D, so I'm going to find what kind of eccentricity I have found in here. GeoGebra has a function called eccentricity, so I'm going to take advantage of it and pass in the path. The path is D. Okay. The eccentricity is 0.03. It's terrible. So the error, it's fine. Okay. Especially for your case, you might find even more than that. So my error is going to be absolute value. Is there an absolute value function here? I don't know. I know it's just the difference between 0.09 divided minus 0.03 divided by 0.09 times 100. So it's going to be a huge error for my case, okay? So it's not going to be that. So again, it's 0.09. I know it's 0.06, the difference between the two, but I'm going to do it just to show you how you're going to do it manually. Divide that by the known value, which is 0.09, and multiply by 100. Okay, I don't know if you can see this or not, but I'm doing the calculation right here in GeoGebra. So the error is coming up at 66%. Okay, it's in my case in here, because the path, let me try to see if I can improve this by moving the point closer. So no, I'm getting a very close value from the circle. Okay, let me see in here the measurements that I have for the near, and the far, and I think the error there is a lot better. Here is where the values that I have. For A, it's this segment, okay, over 2. It's the difference between near and far. So here is a point near, here is the far. So if I take this entire line in here and call it a segment, its length is 30.62. In my case, my semi-major axis, which is the entire major axis divided by 2, it's 15.31. Okay, that's A. C, which is the eccentricity, the difference between the two focal points. Remember, the path has this. The distance between this focal point and where the sun is sitting, which is the other focal point according to Kepler's laws, is 2c, not c. Okay, it's 2c, but or also we can take A, this entire distance, and subtract from it. This is the major semi-major axis, and subtract from it the distance to the near. Subtract this distance, so it's going to give me the value of c. That's what I'm doing in here. Okay, so the value of c, little c, is basically the half the distance between the two focal points. So there is a focal point in here, another focal point in here. Half of that is this distance. Remember, this entire distance from here to here is my semi-major axis. This distance is already the distance to the perihelion from the sun. So if I subtract the semi-major axis, subtract from it the distance to the perihelion, I will find half the distance between the two focal points, which is c in the conventions that we have in here. So this entire distance is 2c. I need just c of that. This entire distance is 2a. I need just half of that, which is a. So it's a minus the distance to the perihelion gives me c. So that's exactly what I'm doing in GeoGebra in here. I'm taking c equals to a minus the distance between s, which is the sun, and the near. Okay, so take this entire distance, which is lowercase a, minus this distance, that should give me the lowercase c, and that turned out to be 1.53. Okay, take the ratio of the two, which is exactly what this formula is supposed to do in this case, to find the eccentricity. It's c over a, and multiply. So it gave me with an eccentricity of 9%. Oh, I'm sorry. Why did I multiply it by 100 in here? I really don't need to multiply it by 100. Not this one. This one. I don't need to multiply. So we need just the eccentricity value, okay? So the eccentricity, it's 0.01, okay? But if I want to find the error, it's this value of E minus subtracted from the other one. So I really need to have this one in absolute. It's going to give me a negative error, but that's not what okay? So it's going to give me a negative 11%. And again, it's just supposed to be an absolute value. So an absolute value, I'm going to take this entire thing and put it in. Okay. So take the absolute value. So it's 11% error. Okay, for my case. Again, for your case, it might be different. It might be more or less because the way that you draw this smooth graph is supposed to be part of the error in this case. Okay, it's going to build an error in here. I really don't know why I got 66% in the first method. I really should have found less than that, but that's fine because it's coming up with an eccentricity of 0.03. It doesn't look like this. The higher the smaller the value, the closer to a circular path it is, and this one is very close from a circle because both points A and B are very close from each other. As I make them very far, then the eccentricity starts to increase. Okay, so that's really how that's why I'm getting a very low value in this case. Anyway, so I corrected it and followed the instructions of the project, where basically you're supposed to find the distance between the sun and the near point on the path, and then the opposite direction is the sun to the furthest direction. From there, you can find the value between the distance between the two focal points. Divide that by the major axis in that case, because that is 2c over 2a. cancel the 2 for my case. I just did C over A, which is the same thing. That gives me an eccentricity. In this case, it looks like it's 0.1, but GeoGebra actually has a precision in here that probably I need to go into the settings in here and change the decimal points to 4 decimal points, and you can clearly see it's actually not exactly 0.1, but it's a value that is much higher than 0.01. 0.09999, so it's still kind of high a little bit, honestly, because it's supposed to be 0.09, not 0.0999 in this case, and the error is still 11% error. Okay, so that's my case, that's the project, and if you guys have any questions, please let me know. Thank you. What is the stop there?